So we have tests coming up. We need to get all boned up for, and be a number of study sessions today of the TAs doing things, and I'll be holding my office hours at 2 as normal. I may be slightly late today to office hours because we have another faculty meeting, and if it runs long, I could be a couple of minutes late, but I'll get there. So anyway, we're looking at structures, and we need to go into more detail and make sure everybody's not getting confused about what's going on with these structures. There's a lot of different ways you can go about declaring these structures and using them in C. And so we want to look at a lot of the different variants of that. You know, the syntax is kind of painful, but you just have to slog through it like everybody else. So I have a little sample here that shows you a lot of the different various ways you could declare structures and then declare variables to be those flavor of structures. So here's the simplest thing you can do. You can say struct and then give it a name like S7, and then you list the fields that live in the structure. And then separately, you could then declare a variable. This var S1 is a variable being declared to be of the flavor struct S7. And I'm intentionally not using the word type there because, of course, types is a separate namespace from the structure. So I'll call it a different flavor of struct. It's not a type, right? So we have the struct being defined up here, and then we have a variable being declared that is one of those kinds of structs, right? And then to access the fields in that variable, you would use the names of the fields that you use when you defined what the struct is. So you'd say something like var s1 dot I is equal to 4, that integer, var dot s1 dot c. These are the names of the fields in the struct that you're using, and the dot is selecting which, you're selecting a field in the struct. So you're putting a Z in that character, and you're putting this big thing into that long or whatever, right? So what is the length of a struct S7? What's the length that's needed in memory to hold one of these S7 structs? Well, that has to do with understanding the alignment constraints, right? So the biggest thing we have in here is a long, which is an 8-byte entity. So the struct laying in memory would have to start at an address divisible by 8 to satisfy that alignment constraint. The overall length of the struct would have to be divisible by 8. And let's see if we need any padding. Well, we got an int here that's 4, and then a character that's 1. So I've used up 5 bytes, and then I bump into this long. Well, that's got to start at an address divisible by 8. So the only way to guarantee that is put 3 bytes of pad after the character so that I've used up 8 bytes before I get to this long. So if I start the struct on an address divisible by 8, and then I use up 8 bytes, then I know this long starts as an address divisible by 8. So I'd have to put 3 bytes of pad after the C. So that's the way this would look laying in memory, right? Any questions about that alignment constraint business? So it's important to understand that so you know how these things actually, where they sit in memory relative to the beginning of the struct. So the other permutations on how you can declare these structs and use them is this one, struct S8, give all the fields, and then down at the bottom, you put the name of a variable that you want to declare. So it's kind of like a combination of the S7 and then the separate statement creating the variable. You can go ahead and put a variable name there at the same time that you're defining what the struct looks like. If you wanted some more flavors, more variables that were this flavor struct, then you'd do something like that, struct S8, give it a name of a variable, right? But you can go ahead and get one if you want. At the same time, you define the struct. So then we have types in C, and of course the types came after the structs were in the language. And so when they stole the concept of user-defined types from Pascal or Algol W, they did it by saying, okay, you have this word type def, and then you say what the type is. In this case, it's struct type is the name of the type I'm creating. And what is one of these? Well, it's one of these S7 structs, one of these guys. So now I could declare a variable var struct type to be of type struct type, right? So I've created a type. Now I'm using the name of the type just like you had int, char, whatever there. The name of the type comes and then the variable name, right? So what is this var struct type variable? Well, he's one of these S7 struct things, right? Because that's what this is. So you got a little bit of confusion there. You can declare variables to be, like this. This variable is a struct S7. And you get the same thing essentially if I said, oh, well, this thing called struct type is a type built out of that struct, and now I can declare a variable from that type that I've created. So there's this kind of bizarre interaction between the world of types and the world of structs. They're separate namespaces. And if you really want to confuse yourself, since they are separate namespaces, you could name the type to have the exact same name that you name the struct. You could really be confused, right? Okay. Well, anyway, so how big is this struct type thing, or the S7? How big is one of those things? How big would it be? Well, 4 plus 1. Oh, I got to have 3 bytes of pad. So that's 8. Now I got 8. So that's 16, right? So if we compile this program, and then we run it, we see it says that the thing is 16 bytes big, which is what we expect, right? Questions about any of this? Other variations on declaring the structs would be like I could create a type def, just say struct. I don't have to give it a name because I'm never going to use it anyway, right? Don't have to put struct S12 or something here, right? I just say, oh, this type def I'm creating is a struct. It has these fields in it, and the name of that type is this something under bar T. So that's a little bit confusing because here at the bottom is the name of the type, whereas there at the bottom, it's the name of a variable of this flavor of struct. So the syntax in C really sucks, but what are you going to do? So hopefully you don't going to get confused by all this. There's different ways you can, get at it. So now we have this type called something under bar T that is a struct that has 2 fields in it. And we could declare a variable to be of that something under bar T type, right? We could say variable name like that, right? And then how would we access the fields in it? We'd say we'd have to pick a field we want. What are the fields in there? Well, I got a zip. And zip is a char, so let's put a character in it. And then I could say dot. What's the other field? Dig. Dig is a integer, so I could put like 6 in there or something, right? So this would be declaring the variable to be of this type, which is in turn a struct. And now I'm selecting the fields in that struct variable, putting things in it. Questions about that? Just like in this one, var s2, which is this guy we declared up here, has a C and an I field, and I put A in the character field. Now notice that we're using the same name, I and C, I and C. Those are the field names in struct 8 and struct 7, but it doesn't matter, right? They're just names of fields that live within this struct, so they don't have to be unique in the whole world. They just have to be unique within the fields that are listed in the struct, right? Okay, questions? So other variants, we could do struct S9, and now what have I got here for the first field of that structure? Well, I'm calling it S, but what type of variable is it? Oh, it's a struct type, which is one of these things we declared up here, right? Which is in turn an S7 struct, which looks like that, which has fields I, C, and L, right? So now I have a variable I'm declaring to be of one of these S9 guys, but it's a pointer to one of those S9 guys, right? So my pointer variable, if I said pointer variable arrow CX, the arrow is a combination thing. Look at the next statement. If I took pointer variable and I dereferenced it, I'd be pointer variable points at one of those structs, right? And that has a CX field in it. So I'm selecting the CX field. You got to put the parens because the dot binds tighter than the splat. And that's not what you want. You want the dereference, then select the field. Well, this is such a common thing that we pass around pointers to structs and they're dereferencing the pointers and then getting fields out of the structs, that we have a little combination way of doing that with this arrow thing. It means exactly the same thing as this splat, dereference it, get the field CX. So if this thing is a pointer to a struct, this thing says dereference the pointer and get this field out of it. It just takes 2 characters to type that, whereas this takes 1, 2, 3, 4, far too many characters to type. So we have a shorthand way of expressing this common paradigm of dereference the pointer to the structure, now select the field within the struct. And that's what this arrow thing is. So pointer variable is a pointer to one of these S9 structs. So we're dereferencing the pointer, selecting the field CX, putting B in that character, right? Same thing that this does. Dump C on top of where we just put the B. And then this one, what is this one doing? Well, pointer variable, dereference that and select the field S, but S is in turn one of those struct type thingies, which is in turn one of those S7 structs with fields I, C, and L. So you see this one saying, take the I field of that struct. So you're burrowing down 2 levels here, right? You're going into the S9 guy, selecting that field, but that in turn is a struct. And now you're selecting the field I out of that struct. So you can go however many levels deep with this craziness you want. And you can have pointers sitting inside the structs as fields of the structs and arrays and all kind of whatever you want, right? So questions about this? Okay, so hopefully this shows you some of the different varieties of ways you'll see these things declared, and you can make your way through the nasty looking syntax. Okay, so now if there are no questions about that, we want to look at some stuff in the textbook on section 3.9, where they talk about heterogeneous data structures. And they're just saying, okay, you know, we could have something that looks like struct. We'll call it rec because in most every programming language in the world, the name for a struct in C, what C uses as a struct, they call them records. They first appeared in the language COBOL back in 1960, and every language since has had some way of declaring a record. So what does that look like laying in memory? Well, it looks like this thing here. You got the I at the beginning of it, takes up 4 bytes because it's an integer. You got a J, takes up 4 bytes. He's an integer. Then you got an array of 2 integers. There they are, taking up 4 bytes apiece. And then after that, you got a pointer to an integer. Well, a pointer, saying this is a 64-bit computer, would take up 8 bytes. So there are those 8 bytes that it takes up. So the overall thing takes up 24 bytes, and the overall length must be a multiple of the largest alignment constraint. The largest alignment constraint is that 8 for the pointer. So 24 is a multiple of 8, so that works out good. Does the pointer start on something that's divisible by 8? Yeah, so if I make sure the whole thing starts on something divisible by 8, then this guy would be at something divisible by 8. This would be at something divisible by 4. All of those. So those would all satisfy the alignment constraints, and it wouldn't have any pad in there in this case, right? So the array that we have as one of the fields of the struct is embedded inside the struct, right? No problem. You can do that. Skip this. We'll come back to it in a minute. So then suppose, get back to the statement there. To access the fields of the structure, the compiler generates code that adds the appropriate offset to the address of the struct, just analogous to what we were doing with an array, right? Remember, we had an array, we had the pointer to the beginning where the array lays in memory, and then we computed the address of the element of the array based on the index and the fact that they were all the same size. Well, now they're not all the same size, so we can't compute where to go based on some index. We have to add an offset for 8, 12, 16 to get to the fields within the struct. So the code coming out of the compiler is going to look like, oh, take the beginning address of this struct and add the offset to it to pick up that field, right? So all these fields are just offsets from the beginning of the struct. So that's what we're going to look at now. What's the compiler generates for this? Well, they say, suppose we had a struct rec pointer. You know, we got that same rec thing we have up there above, and we have a pointer to one of those, and that's sitting in the DI register, the first parameter that comes into some function, right? So if we wanted to copy the R, which is the pointer, to the struct, the I field to the J field in that, what would it look like? And we're assuming that this R, which is the pointer, is sitting in this RDI register. So this says move what the RDI is pointing at to EAX. Well, what is the RDI pointing at? The beginning of the structure is this first field. So the address where the structure begins, if I dereference that, I get that first field in there. That's what it's pointing at. In other words, offset 0 effectively, right? So this is picking up the I, the first field, the contents of the what is pointed at by the beginning address of the struct, putting in an EAX. Now I'm doing a move of this EAX into or past where RDI points. Well, that is the J field, the one after the I. He's offset 4. So this would pick up the I field and stuff it into the J field in the struct variable, right? So it's just offsets to get to the different fields within there, right? I is a 0 offset. He's at the very beginning of the struct. J is 4 in because he's behind that int I. So generate a pointer to the object within the structure, we can simply add the field's offset to the structure address. For example, if we want to generate the pointer, the address of R A sub 1, so R points at the beginning of the structure. I want to go to the field A, that array. I want to get the element 1 out of the array, not element 0, right? And I want to get the address of what that is. Well, if I had 8, the I and the J takes up 8, right? And then each element of this array takes up 4 because they're ints. And I want to take the index into the array, multiply the elements size, right? So if I add an offset of 12, then I've jumped over the I and the J and the A sub 0, and now I'm getting to the address of A sub I 1. So for the pointer in register RDI and a long integer variable in this I sitting in the RSI register, this index that we have here, we can generate the pointer to the address of our field A sub I with this instruction here, right? That's the beginning of the struct. That's the address where it lives. This is the index into the array A. Multiply that by 4, and now add 8 to get past the I and the J that live before the A in the struct, right? So that would give you the address, load effective address of any A sub I, right? Where you put the I in there. In our case, we only got 0 and 1. What the heck? So any questions about that? See how this works? What about this crazy mess here? What if we wanted to say, go into R and select the P field? What's the P field? Remember, he's the one down at the bottom, and he's a pointer to an integer, right? And he comes after the I, the J, and the 2 ints in the array. So he's at offset 16 from the beginning of the struct, and he's a pointer to an integer. So what this stuff is saying is I want to select R is a pointer to one of these structs, right? So I want to dereference that pointer and select the P field. And I want to put something in that P field. What I want to put in the P field, since he's a pointer to an integer, is the address of select the struct, get the field within the struct, and in that A array, the one I want is this index. Whatever the RI field is and the RJ field, add those together and use that for the index into the A array and give me the address of where that lives and put it in that P. A lot of crazy stuff going on there, right? So what would the code look like? Suppose we got, this R thing is in the RDI register pointing at some instance of one of these structs. So 4 past the RDI is the J, right? The RDI is pointing at I at the beginning of the struct. So there's XI. And here's an instruction you haven't seen yet. It's actually a shorthand for an instruction you have seen. Remember when we were doing that move 0 byte long word thing or whatever, those kind of instructions? This is a shorthand combination of one of those type instructions when you're dealing with the A register. We mess around with the A register a lot because he's the one we return function values in, right? So we got some instructions that are just specific to operating on it. And what this thing says is to take whatever's in the EAX register and extend that into the RAX register using right. So convert long to quad word. We're taking the EAX register and taking the high order bit of the EAX register and just sign extending that, boom, all the way into all the bits of the on the left, those 32 bits in the RAX register. So now we've got whatever the heck was in EAX, positive or negative, properly encoded into RAX. And so that's a common thing. So we have this special instruction that just does that, right? So when we put this I into the EAX register, now we've got the proper encoding for I in the RAX register. Doesn't really amount to a hill of beans in this case because we're not going to have a negative index here, right? I wouldn't think, but maybe you could. You're going to add the two together. So maybe it is a negative number that you're adding to the other one to come up with the index. So in any event, we've got the proper 64-bit representation of what we picked up and put into the EAX register, right? So we added those two together, the I and the J, and now we have the proper sum of that sitting in the RAX register. So now we take the beginning of the struct, that's what RDI points at, right? And we take the index that we computed as the sum of the I and the J fields from the struct, multiply it by 4, right? Because they're 4-byte integers. Add 8, which accounts for jumping over the I and the J field, right? And that should be the address in the A array of this index that we computed out of the other two fields sitting in the struct. So now we just move that. And where do we put it? We put it 16 bytes past where RDX points because that's where P lives in the struct. He lives 16 bytes past the beginning of the structure, right? So that's kind of a contrived example, but it's just basically showing you how you get to the various fields by using offsets from the beginning of the structure. Just analogous to an array, right? Only it's heterogeneous fields in there versus a repeating homogeneous cell that's the same size. So rather than computing based on an index, we're just computing where the thing would lie in memory based on an offset. Questions about this? Okay. So now we want to look at the thing we skipped over up here real quickly. Representing an object as a struct. Well, there's a sort of relationship between what you were thinking of in your C++ or Java programming days and the object-oriented kind of stuff and what you were thinking of as an object. And what we're looking at here in C is a plain old vanilla struct. The C branch of the Algol family of languages tree, C branches off of that trunk of that tree and does a number of things different from the other things on the main trunk and the other branches. And then you have languages that derived pretty much syntactically from C, like C++ and Java, those kind of things. They use the same kind of syntax, but they're object-oriented type languages, right? And so they have these concepts of classes and objects that are instances of a class. And so when you define a class, what are you defining? Well, it looks like the data members of your class look just like these things in the struct. And in fact, they just stole the syntax for the struct and reused it in those languages to say, oh, how are we going to define the fields of your class? So structs have a relationship to the stuff you've been doing with these objects, right? But there's some differences, right? The differences would be that in this object mentality, you've got the concept of some methods being associated with this thing that manipulate it, right? Encapsulating those chunks of code that manipulate that. Well, languages that are in the main branch of the Algol family tree accomplish that through what are called modules. The encapsulation mechanism is modules, but C didn't have modules. So when they derived languages from it and wanted to put object concepts in it, they had to mush them all together into one thing called a class because they didn't have a module in C. This will all become clearer when you take 410. But in any event, there's this kind of a relationship here. So you can think of what you're seeing in C++ and Java with those classes as kind of an evolution out of this struct concept where we're not only talking about, well, what are the fields that live there, but what are the functions that manipulate that object, right? So there is a relationship there. In C, of course, we just write a bunch of functions to mess around with a variable that was one of those structs, right? They don't get encapsulated in any particular way, you know. So that's just trying to explain, what would that look like in C? Well, if we had a struct called rectangle, right, that was defining some graphics object on the screen that we wanted to manipulate, we'd say, well, where's the lower left corner X coordinate and the lower left corner Y coordinate, right, for this rectangle. So we know where it is on the screen. And then we got a width and a height for the rectangle. And we got a color. So we know how to draw that rectangle now. We know where the lower left corner is, know how high it is, know how wide it is, what color. So you could render that thing from this information about this thing called a rectangle. And you just build a structure to have all that stuff as one sort of coherent description of the rectangle, right? And so now typically what you do is you would pass around pointers to a variable that was an instance of one of these rectangle things to functions to manipulate. Here they're showing you how you select the fields. We have a variable called R that we're declaring to be one of these struct rectangle things. Remember, you got to put the word struct because it's not a type, right? So you say struct rect, give me a variable that's one of those things. And now I can say R, lower left coordinate, 0, color, all that crud. You just fill it in. But you could also use an aggregate. Remember our aggregates from arrays, non-scalar initialization constants, the same syntax, right? You put the set braces and then you list all of the fields in the struct, just like we listed all the elements in the array and what you want to put in them. So all this junk here, you could concisely say by just using an aggregate. 0 goes in the first field, the lower left coordinate. 0 goes in the lower left Y coordinate. That goes into the width, that goes into the height, and that goes into the color. So you just list them in the order that they're listed in your struct, and you can initialize that variable at the time that you declare it with an aggregate, just like you could with an array. Or you could do it this way if you want. Either way works. Same thing. So now, suppose we have some function called area. We want to pass this rectangle to the function called area, and we want to compute the area of the rectangle. So we have a variable that's the parameter coming in, and here he's a pointer to one of these rect struct things, right? And now what we return is we want to multiply the width times the height. So we dereference the pointer, select the width field, multiply it by dereference the pointer that points at where the struct lives in memory, and get the height field to offset into the thing, right? Multiply those two things together and return that as long as the area of the rectangle. Now, of course, we've already seen that since this is such a common thing where you want to pass a pointer to a struct in, and then you want to get a field within it. We have this shorthand notation for the arrow business, right? Where we, instead of saying paren splat RP paren dot, we could have just said RP arrow dash equal width, right? This would be completely equivalent to that statement there. So that's what our arrow is doing for us. Now we want to write a function that rotates the um, so okay, no problem. You pass me a pointer to one of those things, and then I have a temporary variable that's a long, and I go get the height field out of the thing that you handed to me, right? Using the arrow notation, dereference the pointer, get the field, and now take the width field, stuff it into the height field, take my temporary guy and stuff it into the width. So I'm exchanging the height and the width to do the rotation of the 90 degrees. And the only thing I have to do now is clean up where the lower left x coordinate lives. The lower left x coordinate now is this subtracting the height off of the one I had before. And so I've rotated the rectangle. It's just illustrating using the arrow rather than the sort of primitive form, right? Okay. Questions about any of that? All right. So you can think of these functions that were written. That's kind of like what corresponds to your methods in the Java world or whatever that you've seen, right? Only there's no way that they're kind of tied or encapsulated with it, like in a class, which has aspects of information hiding and modularity that don't exist in C, right? We don't really have anything that resembles modules in C. We fake kind of modules with the ability to do the pound includes thing, but that's a really primitive approximation of what a module does, right? So anyway, C is a more low-level primitive kind of thing. But you see the relationship, hopefully. It's just a bunch of functions. Well, that's all your methods are. They're just a bunch of functions laying in memory. And then you have this game you're playing with a compiler that those are somehow associated with that class, right? Okay, so we've already seen this stuff, and now we want to get down here and do the practice problem. One reason I want to work through this practice problem with you is because it's a lot like problems on the test, and I think one of your homework problems for this week is a lot like this. So it's a good thing to work through and practice this style of problem. But another reason I want to work through it with you is because the stuff in the book has some errors in it. I'll point out the errors that they made in the book. I looked in the errata sheet. There's an errata sheet associated with your textbook. And if you go to the web page for the book, CS App, CS Carnegie Mellon, this is the second edition. I guess maybe there's a third edition that we could put in there. I don't know. Let's see. I don't know if they have the third edition of Rada or not. See if we get a bad URL. Oh, they do have. I don't know. Do they have it or not? Errata for that. Yeah. So they have that. So it's always good to check these errata. There's a error. See, there's a lot of errors. So you should take your text and work through this errata sheet and just methodically work through the book before you read any given chapter and go through and make all the corrections that are in the errata sheet so you don't get confused when you're reading something that's wrong in the book, right? So that's always a good thing when you have a book is to go get the errata sheet. But I don't think it's listed in the errata sheet. This error, but look at it, this problem. Maybe I should submit it to him so you can update it. So anyways, here's the problem. We got a struct called test, right? that has some fields in it. And so let's look at the fields that we have in here. We've got a pointer to a short, not a short. And then what in the heck is this? We got another struct declared inside of this struct. Well, yeah, you can do that. You could have declared this struct outside of it, given it a name, and then declared a variable to be of that struct name. You could have done it in 2 steps, but you can also do it right here. We have a struct that um, has 2 fields in it, and we're naming it as the field S within the test struct, right? And then the last thing we have in this struct is a pointer to a test struct, one of the things that we're defining here, right? And that's a very common thing that you'll see usually last in a struct is a pointer to one of those flavors of structs. That's how you build a linked list. Anybody ever heard of a linked list? Right? Well, this would be the pointer to the next struct, and then the pointer to the next one, and you link all those together in a list, right? So that's a pretty common thing you'll see in programming, building data structures, right? So what we want to do in the problem is they're going to give us some code for some C that is this function that messes around with this thing, but they're only going to give us the left-hand side of these assignments, and then they're going to say, well, look at the assembly language and figure out what the C code must have said, which is real similar to some problems on the test, and I think your homework. So we're looking at the assembly, trying to work backwards to go, well, what must have been the C code to get that assembly, right? So the first thing they want to know is, what are the offsets? And this is one of the errors they make in the book. Well, then not the offsets, but the B question, how many total bytes? So what are the offsets to get to these various guys? P, SX, SY, next. Well, where's the P live? He's at offset 0. He's right up at the beginning of the structure, right? So now if we went to the field named S and then went within that to the field named X, because he's in turn a struct himself, right? Where would that live? Well, it'd live right behind where that P lived. It's a short, so it has to be at an address divisible by 2. This is a pointer. He had to be at an address divisible by 8. So this certainly would be on an address divisible by 2. So there'd be no pad between there. And then the next guy, he would be on an address divisible by 2, right behind him. So the offset of the X would be go past this 8 bytes. So he'd be at offset 8. The offset of Y would be go past 8 plus 2 is 10, and he would be living there, right? Now you get down to this pointer pointing to one of these structs, right? He's 8 bytes. He has to be on an address divisible by 8. So let's look at what we've used up. We used up 8 and 4. Oh, crud. We need to have a pad of 4 bytes sitting in there in front of where this guy starts. So he would be an offset 16. And that's one of the mistakes they make in the book. They say it's an offset 12. They didn't catch that you needed the 4-byte pad. They made a boo-boo. Also, when they list in the book this solution at the back of the chapter to this practice problem, they list how many bytes are in this thing. They say it's 20. Well, that's not true either. It's 24, right? Because you got 8 plus 4 plus the 4 pad plus 8. So it's 3/8. It's 24. So that's wrong in the book. Make the correction in the back of the chapter where they show you the solution to this problem. So now we want to look at the real meat of the question is, here's this assembly language. Figure out what had to be in the C code to get this assembly language. And that's the, real guts of what they're trying to get at with this kind of question. So let's look at it. what does this code say? This is the code for that function, right? This guy here, who's got a function. You got to pass in a pointer to one of these structs, and that's the variable st. So we got st, dereference the pointer and select the field s, and then select the field y within the s, because he's a structure within a structure, remember, right? So where would y live? Y would live at offset 10, right? This would be at offset 0. He takes up 8 bytes, so he's at offset 8. He takes up 2 bytes, he's at offset 10. Correct? Everybody with me? So the code we would expect to see somehow being assigned into the memory location where the struct starts, which is the parameter that is getting passed in here, plus 10. Well, what is this? That's the beginning address where the struct starts. That came in as the first parameter, 64-bit computer. The first parameter is in the RDI register, right? So that pointer to the struct came in the RDI register. So if we go to where that pointer points and then go 8 locations past that, we're picking up memory that contains the X, right? He's immediately after that P pointer at the front. So we're putting X in EDX. Now we're moving EAX, which is our X, into 10 past. Well, that's the Y, right? So that looks a lot like that, right? That's the Y getting assigned to. What are we putting in it? Well, we put st arrow s dot x. So that's what the answer would be, right? Everybody see why that's the answer? We're picking up the X field 8 past, stuffing it into the Y field 10 past the beginning of the thing. So that Y is getting st arrow s dot x put in it. So what's the next stuff say? Well, it says load effective address of 10 past the beginning of our struct. What lives at 10 past the beginning of the struct? Y lives there, right? But I'm getting the address of that location, not the contents of it, right? Load effective address of this. What is that address? Now I'm storing that address into RDI. What lives at the beginning? Oh, P lives there at the very beginning, right? So P is a pointer to an int, right? So I just picked up the address of the Y thing and put it into that P field. So that looks like this. STP is equal to S address ampersand of parentheses st arrow s dot y. That must be what the C looked at like, because that's what I did. I picked up the address of where the Y lives and put it in the P field. Now it says take the address of the beginning of the structure and stuff it 12 past the beginning of the structure. Well, there's a mistake. That shouldn't be 12. That should be 16, because what they're trying to do is they're trying to put it in this next field, and it's not 12. There's 4 bytes of pad there. It's 16 past. Well, what were they trying to put there? The beginning address of the whole struct. So they're putting the address of the struct in this pointer to a struct. So it points at itself. Does that make sense? So the code would look like what? What would the C code have said? Here, it would have said ST, right? because you're getting the beginning address of the structure itself, which is this pointer variable st, stick that in this pointer, which is the next field. Does everybody see what's happening here? Any questions about reaching into these offsets within the structure, getting what's there, putting it in other places in the structure, that kind of thing? How to recreate the C code from the assembly language. If you can't do this, you can't work some of the problems on the exam. So you need to study these types of problems to understand how the code relates to the C code and the way the structure is laid out in memory. Well, I can talk more about this at my office hours today. I can prove that the book is wrong because here's the program that I typed in with all that stuff in it, right? And I generated the assembly language. And notice the 16, not the 12, right? And then I print it out. When you run the program, I print out the size of one of these things, and you get 24, not 20. So there's two boo-boos in there in the sample problem they gave you. Hopefully not confused by that. So correct the book. It's got two mistakes. The question is, this instruction here means load effective address quad word. And so the address that you're loading is RDI is an address, right? Go 10 past that address and give me that address and put it in RAX. So it's getting the address of this location in memory, right? Remember what sits inside the thing here is three things. We just left the other two off, right? So we're just getting what that guy, where he points in memory and adding 10 to it, right? To get the address of the, well, let's bring the code back and what came out of the compiler. There it is. So here's the actual gospel coming out of the compiler when you compiled it, right? Load effective address of 10 past where RDI is pointing, put it in RAX, move RAX to RDI. That's the beginning of the record, which is where that P pointer is, right? And then take the beginning of the structure and put it into the next field at 16, not 12 past. So that is the code that came out of the compiler for that source code, right? And what is the source code saying to do? Get the address of the Y field, dereference the pointer to the struct, get the S field in the struct, which is a turn a struct, and get the Y field out of that struct, right? So that's really offset 10, right? That's where the 10 came from. And get the address of that location. That's what the ampersand means. And stuff it into the P guy. Well, the P guy is at the very beginning of the record, right? So that's just RDI is pointing right at him. So if we take RX and cram that in there, we just took the address of the Y field and crammed it into the P field. Slippery, right? But hopefully makes some kind of sense. So yeah, LEAQ, load effective address. We're trying to get what would be the address of this thing. You don't really want its contents, right? If you're doing a move and you have that parenthesis in there, then you're pointing at memory, right? Like this one, right? These parentheses here is like the splat in C. Says, take this thing and cram it into that memory location pointed to by that address. So the move is referring to addresses in memory. The LEQA is saying, what is that effective address? Load effective address. I don't want the value that lives there. I want the address of that location. 10 past whatever that address is. So I have office hours at 2, but I have a faculty meeting at 1 and maybe a few minutes late, but hopefully not too much, hopefully not at all, but I'll get there eventually. And we can go over some more of this, work some sample problems that are reminiscent of what you might see on the exam and just work through these. And so make those corrections in your text so you don't get thrown off when you're reading through there. There's some boo-boos in this problem. Okay. Any questions about all this magic before we leave for today? So if I don't see you at 2, I'll see you tomorrow at 11, and we'll work through some more examples and reminisce about what all was in the first 3 chapters of the book. Anything before we go? All right. See you later. Bye-bye.